some. Meow. Meow. Trying to get my cat to take the class, but she's not very interested. Say something. Yeah. Guess I'll have to do it then. Yeah, she's a pain in the ass, actually. Well, she's cute as well, but her main trick is to sit there staring at me. Oh, now she looks somewhere else. And then she just goes around yowling for attention. So, but you know, life's a box of chocolates when it comes with cats. All right. Bum, bum, bum. No chance.
Hello.
Where are you? Looks like a woodworking shop.
I'm at work.
Oh, cool.
Oh no, I work at a pet store, and like we have iguanas and Nile monitors and all kinds of stuff over here.
That's crazy. My daughter would love that.
I'm making breakfast for everybody.
Cool. Yeah, my daughter's a reptile nut.
Oh yeah, we got everything here.
That is super cool.
Yeah, we got chameleons, all kinds of things.
Actually, I need to do a little bit more research on it, but one of the examples I discovered for incomplete dominance is, leopard geckos.
Oh.
So I went to this fair with my daughter, reptile fair or whatever, over the summer, I think it was. Oh, shoot, can't remember. Last autumn sometime. And one of the guys was saying, yeah, you can cross these two and you'll get, kind of something in between. And I was like, oh, finally, another example of incomplete dominance. So I got to do some work on that and figure out what that's all about. You're muted, Chance. Can't hear you. Try again. No, I'm not getting your audio, sorry. Unmute it. No, no worries. You just have to listen to my dulcet tones instead. Sorry, everybody. It's kind of part of the deal, I guess. Oh, right. So, before we start on, I want to actually get going on chi-squares first, just because I really want to make sure we go through that really thoroughly, and then we'll do the probability stuff afterwards. Pardon me. Does anybody have questions or want to go over anything related to Mendelian genetics that we covered last week? So monohybrid, test cross, and dihybrid. I want to make sure that all kind of, oops, hit return. Make sure that all fits. I also want to take a sip of my coffee too. So this is always a good time to just, before class, think back through what you learned last class, see if it all makes sense. If it doesn't, then now's a good time to ask. Yum, yum, yum. Now, see who gets, so while people are thinking, see who gets the prize for guessing this movie quote. If I were to take another sip of my coffee and say, oh, sweet manna from heaven, nectar of life. What film is that from? Extra bonus for knowing what the characters are. Anybody? Finding Nemo. 2 crabs at the end on the sewage pipe. Anyway, fill in some space. Oh, I know. It's a classic. How many times has I've watched that? I don't know how many times. It's absolutely fabulous. Okay, if you well, that's what you need caffeine for. Very effective. Amazingly, I actually got all the way through my undergraduate degree without drinking coffee. Don't know how I did that. Didn't drink coffee until I was 20, give or take. There you go. Whole part of my life was missing caffeine. Okay, so if no one has any questions, obviously, if you do have any questions that occur to you, just shout them out. And it certainly is, Calvin. Oh, look at that. What a beauty. Those are fabulous, Chance. Thank you for the insight into your work. That's super cool. All right, so what I want to do today is need to get through all of the probability and statistics stuff. And really it's super important for a lot of ways, right? So one is because we want you to start thinking about not just observation, right? So you make some observations and you go, I think this is happening, right? What we want to actually get you starting on the path is not only I make this, well, I have a hypothesis first, hopefully, make this observation, gather these data, but also, hello, Rose. Oh, is that your pup in the background? Several. Wow, 1, 2, 3. Oh, they're adorable. Man, imagine how much more fun genetics would be if it was just show us your pets day instead. Unfortunately, we have to learn stuff that isn't just pets. I'd like to learn more about dog genetics, actually. Cat genetics is pretty cool too. All right, so back on track. Really, what we want you to do is not just make hypothesis, do an experiment, gather data, but we also want you to start making an argument about whether that data or your hypothesis is supported, right? And in many ways, well, there's different ways of looking at statistics. One way of looking at statistics is it is a very good way of making an argument to convince other people that what you're telling them, the story that you're telling, is correct. It's robust, right? It supports what you're trying to say. And the flip side is also statistics are really useful, and we did a little bit of this in lab, in taking like huge amounts of data and kind of just squishing it down into something that's a lot more accessible and understandable. Pardon me. Right. And so, we're visual animals, without a doubt, and we work well when we have like simple visual stuff to look at. If you ever watch a really good research talk. Actually, the one in my other class yesterday was really good. A lot of it is visual, right? A lot of visual cues kind of to help explain concepts, right? So statistics is really, in my mind, it's those two things, right? Making sense of large amounts of data and having like a fairly simple answer, right? Or understandable answer. And also being able to convince other people of that answer, right? That it is, robust and true, essentially, right? And so, because we're dealing with Mendelian genetics, right? And Mendelian genetics is all about probabilities, right? And that's really like the power of Mendelian genetics and what he worked out. And so, if we have probabilities, essentially we have expectations, right? And that's a word that we're going to use a lot, or expected, right? Because that's essentially the output of those probabilities, right? So if you do blah, 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 based on your understanding, you would expect a certain outcome, right? That's essentially one half of a chi-squared test. Obviously, the other half is what you observe. And the purpose of the chi-squared test is trying to figure out whether any difference between what you expect and observe is due to just random chance, biological noise, variations in your experimental procedures or whatever, or if there's something interesting going on, right? And something interesting would be a deviation, essentially a large deviation from your expectations, which is essentially another way of saying your expectations were wrong, right? And so really that's what we want to find out. Were your expectations correct, right? Do your observed data fit what you expect? Or is there a large difference between the two, your expected and your observed, that cannot be explained just by random noise? Right? Keep coming back to that word or phrase random noise. And it's a kind of an important concept in statistics, right? The idea that you can explain a difference in results, say you repeat experiment twice or 3 times or whatever. If you get a slightly different result each time, that is just by random chance, right? Or random noise. Or is it actually something that's affecting those outcomes of those experiments, right? So that's what we're trying to find out is, do we have because you will have a difference, right? Nothing, you have 2 kids, you're not going to have 50-50 male and female, right? You have 4 kids, you're not going to have 50-50 male and female. There's going to be a deviation from your expected outcome. And so you will always have a difference, right? It's whether or not that difference is meaningful or not. And just, I don't know if was it this class or the other class? I can't remember. Someone told me about how their daughter was the first female in like 3 generations of their family or something like that. Is that you? Yeah. So, no? Yes?
It wasn't me, but it was this class.
Oh, okay. That's right. Cool. Yeah. So I can't remember who that was, but now that is obviously a fairly large deviation from what you would expect randomly. So that suggests that something is going on. What that might be, is essentially another investigation. But that's what we want to find out, right? And so I'm going to do a lot of this stuff on, I mean, all of this is in the PowerPoint, but I'm going to do a lot of this stuff on a whiteboard because it's a lot easier. Well, I mean, it's easier for me. Hopefully it'll be more straightforward for you too. So you get to see the back of my couch again. And let me just grab my stuff. Might have to get up and let my dog out in a second. Okay. Right, so I'm never entirely sure whether it's chi-square or chi-squared. I think it's chi-square test, and that's like this. Never entirely sure if I write it properly. That or something similar. No G's there. Right, and the other way of, let's see if I can bring this around a little bit more. Trying to perpetual fight against glare. This is also called the goodness of fit test, which is a more kind of descriptive name of what it is. I'm going to write out the formula. Hopefully your eyes aren't going to glaze over and like roll back into your head. But this is the basis of what we're going to be doing. And I'm going to go through essentially how we get to all of those different things and how we use it, right? So don't kind of stress too much. I'm just in X. Right, so our outcome is or the chi-squared value, right? And that's not actually the endpoint, right? There's a bunch of bits to this, right? But we'll give you this one first, right? So that means sum of in mathematician speak. And we're going to have our observed, drawn to obs, minus our expected, now again it's just like working out variance, right? In a sense, if you remember from the first lab, working out variance of data points around the mean, right? You can't have a value minus a mean, right? When you have values around a mean, and just leave it at that, because you'll end up with negative values, right? And it's exactly the same for chi-squared. You can't have your observed are going to be above and below your expected, right? If you do enough of them. So you can't just leave it like this, because you'll end up with a bunch of positive and negative values, which when you add them together will cancel out, right? So that's where the chi-squared or the squared bit comes in, right? And all of that is divided by your expected. You know, it's funny, when I first came to A&M, I had to teach in one of the mobile, you know, like those prefab lecture rooms. Don't know if any of you had classes in there. I used to complain all the time about how I only had one small whiteboard. So it's kind of ironic now that I have a really tiny whiteboard instead, right? So you'll just have to be patient. I'm going to take a picture of this before we get off. And so just to kind of hammer the point home, observed, that's what you see, right? And it's actually, these are pretty important terms, really, because they underpin the whole thing. And expected is essentially what your hypothesis or other assumption tells you what you, that's just complicated, should see. Yeah, it didn't come out quite as elegant as I'd hoped, but that'll do. Right? So this number, or these numbers, right, because there's obviously going to be more than one of them, your expected numbers are based off of your hypothesis. Right, so if you're crossing two heterozygotes in a monohybrid cross together to get F2 generation, based on what you know about Mendelian genetics, you would predict that you'll get a 3-to-1 ratio of dominant to recessive out the other end, right? And so your expected would be 3/4 of the total would be one phenotype, 1/4 of the total would be another phenotype. All right. All makes sense? It's all fairly straightforward so far, but we'll get into the weeds in a little bit. Let me just take a picture of that before we get any further. Try and take a picture without my knee getting in the way. Funny thing is, I'm actually using a camera. Look at that. I bet you haven't seen one of those for a while. Actually had that for, oh boy, that's like 12 years old now. It's ancient. Actually bought it in when we lived in Australia after we went to a picnic, friend's kid's birthday party, And it was so hot that it actually cooked the sensor in our previous digital camera. So everything looked purplish pink, which is really weird. Anyway, okay, so I want to go into this expected bit first, right? And so this is really important to get, because obviously you have to figure out what the expected values are to be able to do the whole chi-squared test, right? So your expected values, essentially you work these out as the total of the observed values, right? So if you score, I don't know, 100 total pea plants, right? That's your total observed value, right? Doesn't matter how many of them are the different phenotypes. You want the total number that you observe. That's the first part, right? That's then times by, I don't know, the fraction you expect. Right, so for example, let's try and get this, there we go. Kind of modifying the angle of my laptop with my right knee, which is kind of funny. So for example, let's say we do 2 P crosses, right? So we cross, let's just do something simple. So F1, we're going to cross essentially 2 round pea plants, and we're going to get 3-to-1 ratio of round to wrinkled, right? So essentially what we're saying is we expect 3/4 to be round and 1/4 to be wrinkled. Now, that's before we do the experiment, right? We figure that out ahead of time. So this is what we figure out just based on our hypothesis, right, our expectations. Oh, hello, doggo. My teenage dog has finally got out of bed. And our observed, hello, love. Oh, sorry, doggo cam. Where's she gone? There we go. I've just got to go let her out so that she can have a pee. Be back in just a quick second. I have to get up and let her back in a little bit, but we can do some stuff in the meantime. Okay, so there we go, that'll do. Let's say we score our actual numbers are 1776 round, and what would that be? 224 wrinkled. I like working with round numbers, makes mental math a lot easier. Okay, so this is what we're going to work out our expected from. And this is what we're going to work out our observed from. Okay, so I'm going to put this to the class. Based on this, how many round plants would we expect? Actually, I'm just going to go let the dog in. So I want you to work out how many round and how many wrinkled would you expect? And I'll get back in just a second. Okay, let's see what people have got. Yeah, Gabriel and Rose, that's 100% correct. Tanya, let's figure out where you went astray. Don't know if you have audio. No, don't. I mean, obviously, if you don't want to, you know, kind of go through, I don't want to not make an example of you. I just want to figure out where you got that from so that we can correct it. You there, Tanya?
Yes. So what I did is the observed the 776, I multiplied by 0.75.
Oh, awesome. Great. I'm glad you said that. So that's not right, but it's a really easy fix because what the mistake that, and again, this isn't trying to make an example of you or anything. That's not my intention. I want to make sure you understand it, right? And doing things wrong is actually a great way of understanding how to do things right. Okay, so this is your observed for one phenotype. This is your observed for the other phenotype, right? Now you have to work out your expected from the total observed values, right? And so your total observed values are these two added together.
Okay.
Yeah, beautiful playing, love. Yeah, I mean, that's totally awesome, right? I want to go make sure that I know what your mistakes are because that's how I can help you learn how to do things better, right? You know, if you already understand it, then you already understand it, right? There's not much more learning to be done in the sense, right? But it's when you don't understand it, that's where I can help. Okay, so now you can see if you add these two together, you get 1,000. And so 3/4, oops, of that 1,000 are obviously 750. So always when you're working out your expected values, hang on, let's tip that back up a little bit. You work off your total observed values, right? So if you're doing a chi-square test of a dihybrid cross, right, you're going to be adding your observed values for all 4 phenotype categories together. That will give you your total observed value or values, your sum of the observed. Maybe that's a better way of putting it, right? And so then you can work out your expected from those. Ah, look, I've got a rare lesser spotted daughter. Ta-da! Caught her in the act. Exactly. She's trying to get a jump on her high school genetics. Okay, so does that make sense? Yep, awesome. Okay, I can take a picture of that so I can scrub that off. All right, I'm going to need you to kind of keep in mind the values because I'm going to have to rub these off. So make a note of those numbers down there. And I'll, if I forget them in the next few minutes, which is possible, you can tell me what they are. All right, and sorry about all like the glare on the pictures and stuff. It seems that everything I do to try and avoid glare ends up creating glare in other spots. So it's just kind of the downsides of this, unfortunately. Okay, so now, you know, they don't really. It's kind of funny because they've actually grown up most of their lives in the US. So Sophie was 5 and Evie was 3 when we came to the US back in, I think she was that how old they were? No, it was actually, oh God, don't know how old my own children are. They're 3 and 1, sorry. Yeah, I'm not very good at math. They were 3 and 1, so they, even though Sophie was born in New Zealand and Evie was born in Australia, they didn't really pick up any of those accents because, you know, one of them didn't even really speak very much before we left Australia for the US. So no, but often people think that I'm Australian, which I always think is kind of funny. It's almost like accusing an American of being Canadian. Anyway, so remember our chi-squared equals sum of the observed minus the expected squared over the expected, right? And you have to do one of these for each of your phenotypes or your conditions. So if you have a monohybrid cross, pardon me, you have 2 conditions. If you have a dihybrid cross, you have 4, so on and so forth. Right, and we're using Mendelian genetics because the as a way of working through chi-squared, because it's pretty easy to work out what your expected values are, right? The expectations or the predictions are fairly straightforward, right? So essentially, we're going to do, and again, I want to go through this slowly because I want you to understand how to do it, and it's fairly straightforward, but there's a bunch of different steps. You have to get each one right to get the right answer. So essentially, we're going to do observed minus expected squared over expected for the round phenotype, plus observed minus expected, out the extension over there, for wrinkled. That says wrinkled, just in case you weren't sure. Right? And so now you fill in the values. So we have observed for round was, what was that, 776, I think? Correct me if I'm wrong. Right? Minus 750 squared, because 750 is our expectation based on the total observed times 3/4 or 0.75 divided by 750 plus 224, I think, minus 250 squared over 250. Now, I don't actually know what we're going to get out of this, right? Because I just made these numbers up. So we'll actually see whether this is a result that we would get by random chance, or if there's actually something going on and my numbers are bad. So this is, what is that? 26 squared divided by 750 plus, and that should be the same. Oops. Squared divided by 250. Right, now what I want to get across here, right, and this becomes kind of more obvious the more you do this, right? Essentially, if your expectations are wrong, you would expect a large gap between your expectation, your expected values and your observed values, right? That makes sense, yeah? And so because you do this for each of those conditions, you're going to get, and you're essentially dividing a large number by a large number, right? And so you'll get a large number back, right? And so the larger the chi-squared number, the larger the deviation that your observed data make from your expected, and vice versa. And we'll get into what we're going to do with this chi-squared value in a little bit. We're just not quite there yet. Now, can someone do me a favor? Because I'll be all kinds of clunky if I did this on my laptop. Oh, wow, yay. Gabriel, can you give me the individual numbers first for each of these two? And I'll put 3 point that at the end. What are the in-between numbers? What are the numbers for this and what's the numbers for this? 2.704. Oh crap, I'm running out of space. 0.901. Right. And so your chi-square value is this value here. Okay. All right, I want to give you a few moments for everybody else to have a chance to do that and make sure they understand how we got those numbers. Because sometimes these things take a little percolating to kind of make their way through. I also have to make sure I drink this coffee before it gets cold too. That's pretty important. All right, is everybody with me? And really, really, if you're not, that's totally cool. Just let me know, right? Because that's how we can learn, you know, where we went wrong. Like I said, this is a fairly straightforward thing to do. Obviously, it gets a little bit more complicated the more conditions we have. But you got to get each bit right. Otherwise, you'll end up with the wrong value. Okay. So I'll take a picture of this. And these pictures will all go up. Let's see if I can get my room lights out of the equation. Okay. Pardon me. And once we've done this one, we're doing pretty good for time. I'll give you a more complicated one to do, and then we'll go work through the outcome, right? So now the next thing that you need to know is there's 3 things. How many fingers am I holding up? Looks like a squid. There's 3 things, sorry, that you need to have for a chi-square test result, right? You need your, let's tip this up a little bit. Actually, I wonder if I put this round. No, that doesn't work. Get an extension cable for my laptop. Okay, so you need chi-square value, right? And you need the degrees of freedom, and that will give you your p-value. Now, before I get into what this means, because that's a whole nother bucket of fish, we need to make sure we understand what this is, right? And so essentially, best way that I think of this is, your chi-square value is going to change depending on how many conditions you have. So if we were to do that same chi-square again that we just did, and we had 10 different conditions, each with the same kind of deviation around what we expect, right? So let's say around 24 or whatever, right? From what we expect. If we have 10 of those, let's tip that up a little bit, we're going to have a larger chi-square value, right? Because it's going to be 10 things added together rather than 2. Does that make sense? So the chi-square value depends not just on the variation between, or the difference, right, between your observed and your expected, but it also depends on how many times you do that calculation or how many different conditions you have, right? So that's why we need to work out degrees of freedom. And degrees of freedom, which we often write as just df, because it takes up less space, is your number of conditions, oops, or categories, I guess. I don't know, it really depends on what you want to call them. Oops, no, that's something else. -1. Right, so if you have, like we had, 2, which was round and wrinkled, -1, for the chi-square that we just did, we have the degrees of freedom of 1. How many degrees of freedom are you going to have for a dihybrid cross, F2 generation?
3.
Correct. Why?
There's 4 classes, the 9, the 3, the other 3, and the 1.
Correct. -1 is 3. Right. And Ali got that too. Right. So it's always the number of, essentially the number of times you do that calculation, right? Observed minus expected squared divided by expected. However many times you do that, -1 is your degrees of freedom. Okay. So you need the 2 things, right? Degrees of freedom is 1, and our chi-squared was 3.605 or 905? Let's look at 605. I'm glad people put this stuff in the chat. This makes life so much easier, right? You need those 2 values, right? Because we're going to use those and a couple of scary looking tables to figure out what our p-value is. Okay. Again, stop me at any point. Hey, Soph, could you lift up the kibble from Luna? Make sure she doesn't eat too much. No. Our doggo's on a little bit of a diet because she's getting a bit chunky. So, yeah, she is. Yeah, I gave it for dinner. Use some of the bread on the bread box. No, you don't need to hear about give my dog her allergy pills. All right. Any questions? I'm going to leave those down at the bottom because they're important. Right. And so the next and the final bit that we need to talk about is what a p-value is. Right? Does anybody know what a p-value is? Like, what does it represent?
It's the probability if it's like due by chance or it's within the parameters of what you expected.
Right. Yeah. So essentially, it's a value that gives us a measure of, is this something that if we repeat it again, are we going to get something similar just by chance, right? Is our outcome, whatever that might be, chi-squared in this case, is it occurring just by random chance, or is something going on, right? So essentially our p-value is our probability of getting a given result by chance. Try and get rid of the glare. Essentially, and you can reword that in different ways, essentially get the same thing. And so this is going to be a value, and it's going to be a value between 1 and essentially infinitely small. Right. So if you p-value of 1, that's basically telling you that even if your result was different from what you expect, the probability of getting that result by chance is 100%. Right? So 1 equals 100% chance, of getting that result. And this is all, 1 is the upper bound and essentially 0 is the lower bound, right? Right, you can get extraordinarily close to 0, lots of decimal places, but at 0 is always the lower bound. So it's essentially like a proportion value in a way. Right, so if we have 100% chance of getting that result, we also have, if we have a value of 0, that's equals no chance. So, as I like to put it, something's going on. Right? And that something may be, well, I mean, your expectations are wrong, but then you go, well, why are my expectations wrong? What mistake did I make in my hypothesis, right? Why is that not supported? And then that then leads to other questions and other hypotheses and experiments, and that's how you figure out what's going on, right? So this p-value isn't necessarily the end point. It's merely saying that that particular experiment you did, you're getting a difference that you can't explain by chance alone or random noise alone. It's telling you that something else is going on, right? Does that make sense? That's it's an extraordinarily important concept in biology and statistics. And we haven't even got to the word significant yet. How about that? So essentially, we need to draw a line in the sand somewhere, right? I'm going to run out of space again. Actually, you know what? I'm going to get rid of these. I just have to scroll back up. We can just put those back up another time. And so our line in the sand is essentially if the p-value is less than 0.05. Let's hold this up. Let's turn that down. That's easier. The p-value is less than 0.05, which essentially is 1 in 20, right? Or 5%, whichever way you want to look at it, right? We're saying that this is our line where things become something is going on. Right. And really, we don't say that in papers because we get laughed at by our peers. So instead, what we say is this is significant. And that word, much abused in the scientific language, means one thing. It means that the outcome of our statistical test, be it chi-squared, Fisher's, t-test, ANOVA, whatever, right? The outcome of that statistical test is a result that we're not going to get by chance. Therefore, it is significant. And really, that word significant means it's significant because something's happening, right? That might be something that we intend, right? So, plants grown in sunlight grow better than plants grown in the dark, right? One would expect a significant difference between their heights after a certain amount of time, right? So that outcome is significant because we're doing something to affect it. It also might be the case that the outcome is significant because we do a chi-squared test and our expectations are wrong. So it isn't telling us that what we're doing is, you know, producing an outcome. Like if you were to do a controlled experiment, let's say, it's telling us that our assumptions that underlie our chi-square test are wrong. And so therefore we need to revisit those assumptions and try and figure out what's going on. That's so the what that significant means obviously depends on what test you're doing and the purpose of doing that test, right? For a chi-squared test, our purpose is to figure out if our observed data match fairly well our expected data. Therefore, our expectations are correct. And if we get a p-value that's significant, it's telling us something's going on. Therefore, our expectations are wrong. Okay. I want you to have a little, you know, kind of cogitate on that for a second. Got more coffee to drink. And think about that. If you have any questions, let me know. I'm going to turn this light off because it's hindering more than helping, I think. And again, I know that some of you have done like biostats and have a pretty good familiarity with what we're talking about, but it's important that all of you get it. All right. Any questions, queries, general befuddlement, any of that?
I just wanted to share because when I was introduced to this, it was confusing because the lesser the amount, like the lesser the p-value, it was more significant. So it's kind of like, why is it significant if it's a low value? And you have to get used to that kind of, like, I don't know, put it in your mindset. That was confusing for me when I got introduced to this.
Yeah, that's a really good point. I hadn't really thought of it like that. Yeah, but the smaller the number, the happier you are, right? Which is kind of usually like, you know, smaller your bank balance, less happy you are, right? Actually, it's more like credit card debt. Think of it that way. The smaller the number, the happier you are. So, and also it's really important to get what that number means, right? And so this is the really important part. The smaller the number, the larger the likelihood that the outcome is not due to chance, right? That it's, or the smaller the number, the larger the likelihood that it's due to something else, something that you're doing, whether you're doing something wrong in a chi-squared test, like your expectations are wrong, or you're doing something right in a controlled experiment, i.e. your treatment is having an effect, right? And so the less likely that that difference that you're seeing is due to just chance, the more interesting it is. Right, so a great current example, you know, would be, actually I read a news article about Israel, right? They've got this huge vaccination campaign going on, at least for Israelis. And they've actually got enough data now to get a sense that of how well the vaccine is working, right? And so they looked at how many old people were dying or getting the disease after getting vaccinated versus beforehand and versus places that had lower rates of vaccination. Pardon me. And it was something like, I don't know, 300 people over the age of 65 got corona or COVID after being vaccinated versus around 5,000 that got it that hadn't been vaccinated, right? And so if you're to do a statistical test on those, and it'll be probably a lot more complicated than, you know, what we're doing, you're almost certainly going to get a very, very, very low chance that that difference occurred randomly, right? And so in this case, the thing that's going on is you're giving people a vaccine. right? If that vaccine had no effect, right? There's obviously different ways of doing that statistically. Then you would expect fairly similar numbers between the vaccinated and the unvaccinated populations, right? And so really you want a smallest possible chance that that difference occurred randomly. So yeah, that's a really good point, Tanya. And it's kind of, it really helps getting those perspectives, because obviously I've been doing this for a long time, and when I actually, it's lost in the sands of time, right? When I first learned about this stuff, like 20 years or so ago, I think it was my PhD supervisor, not literally, but metaphorically pounding it into my head. Matt, we need bloody understand this, because it's important. Anyway, that was me trying to learn how to do ANOVAs by myself. You kind of threw me into the deep end there. So let's bring up screen. All right, so shoot, this is taking a while. Okay, we'll have to do the, I absolutely loathe this chart. Let's see if I can find a chart for you. Get off. Actually, you know what? Where's, yeah, this one will do. We've got a chart in here, because you're going to need this for, I think, exam 1. Yeah, I need to log in. Come on. All right. Hey, there we go. All right, so we've got these two different charts. You can use whichever works best for you. Some people, this works really well. I'm like, my look at that, my brain goes in different directions. So I like using a chart instead. Right, so you're going to have two numbers. You're going to have your chi-square number, 3.605, and you're going to have your degrees of freedom number. In our case, 1. So the very first thing so they're looking at this, can you all see this okay? Looking at this table, and you can find copies of this all over the place. I was actually kind of looking, but I ended up giving students one which was completely wrong once, which is not good. So there's 3 different things on here, right? Because we need 3 different values for our full chi-square result, right? We need our chi-square, we need our degrees of freedom, and we need our p-value, right? And this table has all 3 things. So we have our degrees of freedom down here, right, on the left column. We have our p-value or probability level up here on the top. And we have our range of chi-square values in here, which thankfully someone else calculated for us, right? So what we're going to do is essentially we want to see whether or not for a given degree of freedom, our chi-squared value is higher or lower than the number underneath the 0.05 kind of column, right? So this is the column of significance, right? If our chi-square value is larger than the number in this column, it's kind of going over that away to your right, then we get a significant p-value, right? If it's over here, we got basically a 1% chance of getting that result by just random chance, yeah? If that number is higher than this number of significance, that's not a real term, by the way. If it's not high, if it's smaller than that number, right, then we're basically saying that even though we do observe a difference, that difference is not meaningful, right? It's just due to random chance. Okay, so this is the column that matters. Okay, questions? Does that make sense for people? All right, so essentially this column is our line in the sand, right? This is the one that that matters. And so what you do is you go, okay, what are my degrees of freedom? In this case, it's 1. And so this first row is what you care about. And then you take your chi-square value, which is 3.605, right? And you go along here and you say, is that number smaller or larger than this number here, 3.841? And in our case, thankfully, I didn't screw up the numbers too badly. In our case, that number is smaller, right, than 3.84. It's 3.60, 3.61 essentially. And so our p-value is greater than 0.05, not by a lot, right? But this is a line in the sand, right? It's only matters if you cross it. Doesn't matter if you're close to it. It's only once you go over it that you can call this result significant. And so there is no significant difference. This is kind of the formal way of doing it between our observed values and our expected values. Even though there is quite a large difference, that difference is still within kind of the boundaries of what you would expect to get by chance. Essentially, it doesn't mean anything, that difference. It's just biological noise, or I don't know, various kind of oddities or whatever in how you collected the data, right? It's not significant. So again, just to reiterate, you need 3 things: degrees of freedom, 1 in this case, chi-squared value, and you'll give at the end of that the p-value. And so in this case, you would go, okay, degrees of freedom 1. My chi-square value is smaller than this value here. Therefore, my p-value is, let's bring up the chat. Dang it, where'd you gone? So in this case, your chi-square, if I can spell square, equals 3.605. df equals 1. And your p-value is greater than 0.05 equals not significant. Okay. Now, in what we have left, okay, let's give you another test, and I'm going to give you a few minutes to work this out, and then we'll spend the rest of the class going through the result. Okay. So let's think. Dihybrid cross. F1 times F1. And so you now automatically know, okay, those F1s are going to be hybrids, right? You have 2 genes. How many phenotype combinations? 4, right? Because it's dihybrid cross, right? So you already know a bunch of information about what's going to happen here, because this is always going to happen the same way. And okay, we're going to have 960. I don't know. Shoot. Grumpy dwarfs. Bum, bum, bum. Probably should just skip the descriptions, right? And okay, F1, this is going to be Okay, and I've actually typed these out, so you can work this out from the phenotype combinations. This might actually be a bit of a challenge to do in the next 10 minutes, but we can give it a shot, right? I've actually written them out in the same normal order that you would expect to get your F2 generation, the 9 to 3 to 3 to 1, right? So don't make any assumptions about the order. You actually have to go back and look. Okay, I've got grumpy dwarf times grumpy dwarf, right? And so these are the dominant traits, the dominant phenotypes. Grumpy and dwarf are, and this is, from Snow White, 7 dwarfs, obviously. I don't know actually if you have happy non-dwarfs, and anyway, it doesn't matter, right? That's a tangent that we can't afford, right? So you need to look at this and go, okay, what would I expect to get? You'd expect to get grumpy dwarfs out. That's going to be the dominant phenotype. You expect to get the opposite, which would be happy non-dwarfs, right? That's going to be the recessive, and you'll get combinations of those two. So you get grumpy and non-dwarf and happy and dwarf, right? Those are going to be the two non-parental combinations of phenotypes. Okay, so first, what are you going to do? What are your first steps in doing this chi-squared? You can do one of two things.
Would you add them all up to get the total?
Yeah, exactly. So you're going to do, oh, what did you miss, Gabriel? Okay, we're doing a fairly silly chi-squared test. Oops, that's a bit too far. Using grumpy dwarfs. Gotcha, Erica, just give me a second. And I've given you both the cross that we're doing. I've given you the phenotypes, the dominant and the recessive, and I've given you the outcome of that cross. Erica, what's up? I don't actually know what to do once someone raises their hand. Oh, okay. Oh, no worries. All right. So yeah, exactly. What you do first is you work out their expected values, right? And you do that by doing two different things, right? One, what Tanya said, you add together all of these values together, right? So this is going to be your total. Oops. Change that. That's going to be what? 960 plus 150 plus 1. Oops. What's the other one? 350. Did anybody work that out for me? I could probably do it mentally, but it would take, we don't have a lot of time left. Yay, all right. So keep that value. Thank you, Christina. Keep that value in mind, right? What's the other thing that you need to do to work out your expected values? What else do you need, right? Remember, it's total observed values times what? What do you need to times that number by for each of the 4 different categories?
Expected values.
Well, that's what you're calculating, but what do you need to calculate the expected values? What would you expect in the F2 generation of a dihybrid cross? What
Probably
ratio
need the
would you expect?
fraction.
Say again?
Hit the fraction. So it'd be a 93 to 3 to 1.
Right,
ratio.
totally. Exactly. So if you, okay, so let's turn this around again. What would you expect for, I'm going to regret using these particular categories now. How many grumpy dwarfs would you expect? So it'll be, let's type this out, grumpy dwarves. Yay, thank you, Gabriel. You did that way far. Oh, actually, shoot, I don't know which one's right now. Give me a second. So that's going to be 1680 times 9/16, whatever that is in decimals. Right, so 9 divided by 16, 0.5625 times, oh, that's no worries at all. What's the other one? 1680 equals 945. Yeah. So Tanya gets the virtual prize for that one. Okay. Now you need to do that for all the other ones, right? So essentially the happy dwarfs will be the same again, 1680 times 3/16. And then same for the other non-parental combination. And then the recessive will be, what is that? 1680 times 1/16. Or essentially 1680 divided by 16. Okay, so work out all those numbers. So we've got grumpy dwarves equals 945. Happy dwarves. Really regretting. Why did I use something with W in it? So how many happy dwarfs would you expect? Okay, Christina. Oh, okay. So good question, Christina. Essentially what we're working on is a dihybrid cross. Right, let me just type this in for a second. So a dihybrid cross in the F2 generation, right? So if you go all the way back up, where'd it go? Here we go. Our F1s are grumpy dwarfs times grumpy dwarfs. Our F2s are these values here, right? And so because it's a dihybrid cross, the F2 generation should always be, if our assumptions are correct, a 9:3 to 3:1 ratio of dominant to recessive dominant to dominant recessive to recessive recessive phenotypes. That's where the 9:3 to 3:1 comes from. Does that help? Cool. Okay. So the useful thing here is you don't have to do this one again. We've now got I don't know, grumpy non-dwarfs. That's probably a hyphen there. Is exactly the same as the happy dwarfs, right? Because it's the opposite, right? So it's the other 3/16. So that's also 315. And then the happy non-dwarfs is, what is that? That's going to be 1680 divided by 16, or times 1/16, which is essentially the same thing. And so that's 105. Okay, so these are our expected values, right? So we have expected is 945, 315, 315, 105. Observed equals 9. Let's just copy that. Haha, that's typing. Oh, bloody hell, Tanya, I can't work that fast.
I did it a long time ago, but I don't know if it's correct because it's a big like chi-square.
Okay.
So I'm still waiting for what y'all get.
Okay, so we only got a couple of minutes left, so we don't have time to go through this completely. We'll finish this up at the beginning of next class, and also have a very quick run through the probabilities part. But what I want all of you to do is to do this by hand, right? And that goes for you too, Tanya, even though doing it in R is super, super cool. What I also want you to do is, oh, you even done the same. Oh, that's cool. Happy non-dwarfs being HND, I guess. I want you to do this by hand, right? So because it's important to understand what you're doing, right? So essentially you have to do your observed minus expected for each of these 4 categories. So it'd be 960 minus 945 squared divided by 945 plus 150 minus 315 squared divided by 315 plus, right? So I want you to do that for all of those. Add that together, get yourself a chi-squared value, and then look at this column or this table over here. This is in the exams and quizzes folder on Blackboard. Figure out how many degrees of freedom you have, or just look at Tanya's outcome, and then see where that number lies along the relevant row. And then we'll quickly go through that again at the beginning of next class so that everybody's up to speed. Okay, we're pretty much bang out of time. Look at that. The clock literally ticked over while I said that. So I'm going to call it a day for today, and we'll pick this up on Thursday. But really, truly do this practice, because this is how you get good at doing something, is by doing it lots of times, and see what you get. And we'll go through it again in class on Thursday. Okay. And also, you can just make these up, right? I just made this up off the top of my head, obviously, because it's not a kind of standard textbook example. But you can do this for all of that stuff. You can actually go through the Mendelian genetics PowerPoint, and there's some actual data in there from p-crosses that you can use too, if you wish, right? Do those, practice them, get comfortable doing them, and you'll be fine, right? Again, it's relatively straightforward, but you have to do everything exactly the right way, okay, for you to get the right outcome. Cool. All right. Thanks very much, everybody. I'll post these pictures in the Zoom and chat in a little bit. Just go get lunch for the kids first. And I'll see you either tomorrow in lab, or I'll see you on Thursday. Have a great day, everybody.